Hey, it's Pavlos, and I wanted to get this physics video to you before I get to go on a trip. So first of all, disclaimer: I'm not a physicist. I have an undergraduate ability to do physics, and after that, I just follow the subject as a personal interest. So with that out of the way, let's go. So why, or what's the reason of talking about physics? It's of course the technical part of the subject is done by experts, and you hear about fairly exotic things like the Higgs or the supersymmetry or dark energy, dark matter. We're not going to talk about this stuff directly, but more recently there is new interest in the fundamentals of physics that any person could be interested in philosophically. Like, what does it mean to take a measurement? Is quantum mechanics true, or is it a matter of what we know? Is the universe observer dependent? Are there many worlds? These sorts of things. And in particular, recently there's been two physicists who have a kind of popular outreach program, Sean Carroll and Sabine Hosenfelder, and they've been very I've been influenced a lot by what they put out, and I'd like to make a sort of this video is motivated by what they've made. So in particular, the question I want to ask is, does what I see professional physicists doing is pursuing the idea that physical laws are beautiful or abstract or mathematical, or that there is beauty in the math and so on, and in particular whether that is a good idea. I think it's not. I think first of all, I don't find the standard model particularly beautiful. I think it's messy. It has some 17 particles instead of having, I don't know, 5 or 7, with relatively arbitrary properties. And they're not arbitrary, there's a reason for them, but they're not, I don't find it particularly elegant. If I was some kind of super being programming the universe in the simulation, I wouldn't be programming the standard model. I'd be programming something much more simple, and it would emerge. So maybe it's because I don't understand physics, but I don't find it beautiful, but it means nothing to me. Same with supersymmetry. People are apparently claiming that it's beautiful and amazing, but they haven't been able to share that with the general public. They haven't been able to make predictions either, so much with that. Supersymmetry string theory is another one. I have no idea if people literally mean that there are strings of material, or whether they mean that they observe some mathematical regularities which are vaguely reminiscent of harmonics. I think they mean the latter, but they've not been terribly clear. So those sort of abstract forms of beauty haven't been a particularly amazing guide to what the universe actually does. But I think even for a lay person, there are some principles, some very good hints that time and again turn out to be true, that we can use without mathematics to kind of guess what might be right and what might be not so right. So I'm going to talk about roughly 6 of them today. So these are principles, these are things that are true time and again, regardless of the specifics, that might guide us into how nature actually works, what tends to be true and what tends to be true as a pattern and what doesn't. So the first one is, the first general principle is that things are conserved. So certain things are conserved. You know this from school, that there are conservation laws. There's conservation of energy, of momentum, of electric charge, and so on. Now, this is a relatively new insight. This insight is only a couple of hundred of years old, and the ancients didn't have it because things didn't appear to be conserved. But once people started counting energy, well, it didn't look like it was conserved. But in the 1800s, they started counting energy correctly, and they included heat and various other forms. And at that point, they said, oh, it's actually a reliable principle that energy gets conserved. And they started using that as a reliable predictor of what a physical system would do. So once you know that the energy is conserved, you can just reason without understanding the mechanisms, the specifics, and if it can behave in a way that conserves energy or in a way that doesn't, you know for sure it's going to conserve it. The same with momentum and other such things. And in the 1900s, we've got an amazing theoretical result from Emmy Noether, known as Noether's theorem. Noether was a mathematician and a woman, which was like she was passed over because of that at the time, and so the result is not known to many people today, but it's one of the most amazing results in physics, that whenever the universe has a continuous symmetry, a local continuous symmetry, there is a conservation law. What's a local continuous symmetry? So time is a symmetry, so if I throw my lens cap, it went up and down, and I could play the going up and the going down, you wouldn't know the difference. The laws of physics are symmetric in a microscopic sense, going forwards and backwards. There are other symmetries, so if I turn here or there, the laws of physics haven't changed. So this rotational symmetry is what results in conservation of angular momentum. Obviously, if I start and stop, the same is conservation of linear momentum. And there are some more technical ones. There is a symmetry that results in conservation of electric charge and so on. So that's knowing that there are local symmetries and each one of them has a conservation law. That's an extremely reliable guide to know what is going to be true or not. So Noether gave us this theorem that every such symmetry means that some quantity is going to be conserved in the long run, or all the time actually. And so that's been an extremely reliable guide. What does it do for us? Well, there are some obvious elephants in the room here. So one of them is we know that information is conserved. We know that the laws of physics always preserve information, but we don't have the obvious symmetry for that. We don't know the what to make of it as a conservation law. The other one is that we have two things that don't appear to be conserved. One of them is entropy, so the universe gets more and more disorderly, and the other is that the universe is expanding, space is expanding everywhere. And I speculate that conservation of information has something to do with entropy. So I speculate that the second law of thermodynamics could possibly be recast as a different formulation where it's based on conservation of information. That would be the topic of a different video. And it could be that the expansion of the universe, which is like a one-way process, where is the conservation? So it could be that it's something as simple as saying the energy of the vacuum is constant, but it could be more than that. So it could be that we come up with an emergent theory where we learn something from reasoning about the conservation law. So the first one is conservation law. It's a very powerful principle for how the universe behaves. The second one is the somewhat surprising result that everything that can happen happens. In quantum mechanics, everything that could be a possibility actually happens. So that's not especially revolutionary. So Feynman taught us about that back in the 60s or 50s, wherever. So and it's why photons appear to travel in a straight line, but also why they appear to interfere. So when you send a photon from A to B, it checks all the possible paths. It could go straight, but it could go kind of sideways, and it could go through an opening here and another one over there. It could be reflected. The photon takes all of these paths, or rather nature takes all of these possible paths into account and adds them up, positively and negatively. That's called interference, and finds the combined path, which in classical situations appears to mean that the photon goes straight. But we arrive at this result by counting all the paths. That's an amazing result, and at the time it was kind of quite revolutionary, but I think it's sort of been forgotten. So we need to look back and say, well, if there's a question how nature behaves, it probably behaves in all the ways simultaneously, and then they get added up. Some of them cancel out, that's negative interference, some of them remain, that's the phenomenon that we observe. So in particular, we have today a phenomenon called quantum measurement, which is, it's not it's an old phenomenon. It's the behavior that when a quantum system changes from a sort of single particle or another very trivial system into a macroscopic system, it stops being superimposed. It appears to make a probabilistic choice and go one way or the other. The question is, why does this happen? So a kind of rubbish answer is that, well, there is a different rule that says when you make measurement, you choose the amplitude square and that of some function, and that's what happens. So that's kind of rubbish. And instead, there is a much better answer that says there's a phenomenon called decoherence, where the universe continues to just add up all the possibilities. So the photon could interact with an electron over here or over there or the next place or somewhere else. So it could have all of these interactions with, for example, the photon could go into my camera and interact with like any number of electrons in the detector. It could do any of these things at the same time. They all get added up as positive or negative amplitudes, and then they get amplified by the electronics of the camera and so on, so that some of the possibilities get extinguished. Their conditional probability goes to zero, and other ones the probabilities become only zeros and ones. So you end up with there's still all the possible outcomes, but the subsequent outcomes, like the one piece of the macroscopic system interacting with the second, just amplify this result. So you end up with the macroscopic system being in one or another position. And that phenomenon is called decoherence, and the belief that this is how the world works is called the many worlds interpretation of quantum mechanics. And I don't like many worlds because if you think about classically, if you think that the universe splits in two, depending on which way a quantum event happens, that's mind-boggling. But if you think that, we already knew that even in a trivial case, the particle takes all possible paths or all possible branches of a Feynman diagram, if you know what that is, that was already a known result. And the obvious way to continue with that is to say that this continues up to the macroscopic level, and there's one a branch of events where the macroscopic world has like a certain configuration. There's another branch where it has another configuration. You perceive one of them, and there's nothing weird about it at all. It's just how nature is. So in general, I think it's an extremely powerful intuition that the number two intuition is anything that can happen happens. All these possible ways that are permitted by physics just happened, all of them, and they get added up. Where they're inconsistent with each other, they interfere destructively, so they cancel out. And what you get is you get to observe a part of the result, and that's the world that we see. More of this later. Now, the third great intuition that we have is that the universe is extremely observer dependent. So Einstein taught us that in the early 1900s, that there is no such thing as an absolute position or an absolute velocity. There is also no such thing as an absolute time. If there's no such thing as position or velocity or time, that means there's also no absolute definition of events. So if you think that an event has happened, from your point of view, from another person's point of view, it has not happened, because time can be very stretchy. So maybe it hasn't happened yet. But because time is very stretchy, like a lot, the event could never happen. There could be an extended period where people disagree if some event has happened. And that's one result from the point of view of special relativity and also general relativity, that the universe is very observer dependent. But you can take the same kind of thinking to what we've just discussed in quantum mechanics. So why do we perceive that the universe, that when that Schrodinger's cat is either asleep or awake, or why does the photon appear to be detected in one or another position of the camera sensor and not everywhere? So the answer is that, well, the universe is observer dependent. So the universe has a space of possibilities that evolves generally abstractly, but you observe only part of it. So from your point of view, the photon got detected over here. From another person's point of view, the photon could have been detected elsewhere. And that's just an insight that the universe is completely observer dependent, and whatever theory you come up with, you have to come with the only theory you could test is an observer dependent theory. So you could have some kind of conceptual philosophical idea that there are many worlds, or that there is a different kind of universal truth, but you can't say that in a scientific sense, because the time and again the observation the principle has been that the universe is observer dependent. It doesn't seem to have like an absolute preferred anything. And you can observe the universe one way, someone else can observe the universe another way. A particularly striking example comes from the study of black holes, where apparently it's possible for one person to fall into the black hole and not notice it, because of the way that space and time works for them. They just appear to be they can see that they're approaching a black hole, but they don't notice that anything has happened to them. From the perspective of someone far away, they have fallen onto the horizon surface and they've been destroyed. And that's surprising, but it's only surprising. Well, it's not surprising given that the universe is observer dependent. So that notion that it's observer dependent is a very powerful intuition that can guide many, many things. Another, so let's go into number 4. The fourth very strange principle is that every surface, if we look in the world around us, you may have heard of, or rather, yes. If we look at the world around us, every surface is a hologram. So you may have heard of something called the holographic principle from kind of far-out physicists like Susskind and Maldacena, and that theory is phrased in terms of black holes and horizons and kind of weird things, where they claim that, well, you could replace the bulk of the universe, all of the inside of the universe, with a surface out at infinity, which has fewer dimensions, and all the particles are somewhat rearranged as something else, which is in 2 dimensions on the boundary, and that gives rise to all the same phenomena. Or they say that something similar could be done on the surface of black holes. But it's a general principle that any surface in the universe should be a hologram. So what is a hologram? A hologram is a surface that can generate, let's say, all the signals that pass through it, all the fields and all the particles. So imagine that around me I have, at arm's length, a really, really good computer screen that can generate all the light from kind of this outdoor sphere, and as it has all the intensity of the sunlight, which there isn't any much of, but So imagine that I'm surrounded by a really, really good computer screen with really amazing processing. And that means that everything away from me, you could say that it's equivalent to, instead of being out there, you could say that there is a surface around me that generates this whole picture. And of course, we can kind of easily imagine that with light. But then you'd say, no, this is just an imagination, because like, what if some object, like this twig, comes and kind of tickles you? But actually, this twig is made of particles, and if I have a good enough computer screen that can generate all the electromagnetic and electron fields and baryon fields and so on correctly, and it has enough processing, then it could start generating these fields at its surface that would cause this solid object to come towards me and actually touch me. And if I extend my arm out into the imaginary surface, then I could say that, as I pass through the surface, my hand kind of disappears, but the surface reproduces all of the physical impulses that cause my neurons to think that I have my hand, and when I bring my hand back, the reverse happens. So any surface could be a holographic surface. Again, that's by no means a new principle. That's if you have a theory based on fields, and you take those fields seriously, like the electromagnetic field and so on, even the classical one, Maxwell's fields. If you take those seriously, then it has to be that any surface around anything, all at once, any surface anywhere, can be thought of as a complete abstraction of what happens beyond that surface, because the only way to interact with the universe is with changes in fields that pass through some surface around you, and everything therefore is a hologram. So if you hear some strange theory like the holographic principle, just see that it's not especially physicists might be using interesting special cases to gain some insight or to prove a point, but any surface will do. Any surface has this holographic property. Okay, now for the general insight number 5. So this is that the physical laws, the laws of the universe, apply all the time, everywhere. So there isn't, a physical law for small things and a physical law for big things. There isn't a law for gravity and another law for quantum mechanics. There isn't a law, it may appear that way because we don't have a good enough theory for all of these things, but time and again we found that when our laws didn't apply universally, that was just a lack of, it's because our physics was an approximation, and whenever we did a better job of that, we ended up with a theory that applied everywhere. We've never found a fundamental theory that has only limited applicability. If it appears to have limited applicability, it means that it's an approximation. So, coming back to the so-called measurement problem in physics, so there is apparently there is this idea that if you don't measure the particle, it behaves quantum mechanically, or if you have very few things, just one particle, just a few particles, and preferably they're also very, very cold, then they behave according to the laws of quantum mechanics. So you might have like a whole bowl of fluid or a superconductor, and the whole thing behaves quantum mechanically. But then if it gets hotter, or if you have like an interaction with a big messy system, then it behaves classically. And that's nonsense, because as I said, the laws, the physics should apply everywhere all the time. If it appears not to do, then the physics isn't good enough. So it's not a matter of philosophy that it's not a matter of whether it's intellectually satisfying for us to have a single theory that explains what is a quantum measurement or what is quantum gravity. The purpose of quantum gravity is not to predict how really tiny things are going to pull gravitationally on other things. This effect is going to be so small it's going to be irrelevant. But the problem is that any particular physical theory has to apply everywhere to everything all the time. And in the case of quantum gravity, you want one theory that always applies. You don't want to have to choose, should I use this theory or that theory? Because then the theory, I mean, of course, you might know empirically which theory is right, but the theory should tell you itself, in theory, when it is applicable. And preferably that should be all the time. Same with measurement. Currently there is a rule that says, usually you use the wave function, but sometimes you take the probability, you get rid of the wave function and you take the amplitude square, and that's your probabilistic result. That's just a bad theory. So it's not just a philosophical problem, it is just that, if that's an effect that happens, which it does, then the theory should explain why it happens. And the theory itself should tell you where, how to transition between one kind of phenomenon and another within the terms of the theory.